Hi guys, myself Sachin. I'm from SVCE Bangalore, 4th SEM ISC. Now we'll discuss about time and space complexity and analysis of algorithm. So now we'll discuss about introduction, performance analysis, estimation of time and space complexity of algorithm. Understanding the efficiency of algorithms is crucial for optimizing their performance. Time and space complexity analysis helps in predicting how an algorithm will perform in terms of time and memory usage. So we can see time and space complexity from the above graph. So the graph depends on the big O and the 2 power n values. Now we'll see about what is time complexity. Time complexity measures the amount of time of an algorithm takes to run as a function of the input size. It gives an estimate of the worst case scenario from the algorithm's execution time. Common notations used to represent time complexity are big O, big omega and big theta. And these big O, big omega and big theta are represented in the graph, and you can find the time complexity using the graph. Understanding big O notations. Big O notations represents the upper bound of the algorithm's time complexity. It denotes the worst case scenario of the algorithm's execution time. Example, big O1 for constant time complexity, big O(n) for linear time complexity. Now let's see about the big O notation summary. So big O1, it is a type constant. It is used in hash table access. Description remains constant regardless of the size of the data set. Now we'll see about big O log n. It is logarithmic. It is used in binary search of an sorted table. Increased by a constant, if n doubles, the time performed increases by a constant smaller than the n amount. Now we'll see about big O smaller than n. It is sublinear. Search using parallel processing performs at less than linear and more than logarithmic levels. Now we'll see about big O n. It is linear. Example, finding an item in an unsorted list. Description, increased in proportion to n. If n doubles, the time to perform doubles. Big O n log n. It is n log n type. Example, quicksort and merge sort. Description, increases at a multiple of a constant. Big O n square, it is quadratic, and example are bubble sort. Increases in proportion to the product of n star n. Big O c power n, it is exponential. It is used in travel salesman problem using dynamic programming. Increases based on exponent n of a constant c. Now we'll see big O n factorial. It is factorial. It is used in travel salesman problem using brute force. So it is increased in proportion for the product of all numbers including example 1 star 1, 1 star 2 examples are found. Now let's see about what is space complexity. Space complexity measures the amount of memory and algorithm required as a function to the input size. It provides an estimate of the worst case scenario for the algorithm's memory usage. Common notation used to represent space complexity are big O and big theta. We'll see about relationship between time and space complexity. Time complexity and space complexity are independent on each other. An algorithm can have different time and different space complexities. It is possible to optimize one at the expense of the other. Now let's see about analyzing time complexity. Analyzing time complexity involves counting the number of operations performed by the algorithm. We focus on the dominant terms that contribute the most to the overall time complexity. Common operations to consider are comparison, assignment, and arithmetic operations. We'll see about analyzing space complexity. Analyzing space complexity involves counting the amount of memory used by the algorithm. We consider the memory required by variables, data structures, and recursive calls. Auxiliary space complexity refers to the extra space used apart from the input. We'll see about best, worst, and average case complexity. Best case complexity. Best case complexity represents the minimum time or space required by an algorithm for any input. Worst case complexity. Worst case complexity represents the maximum time or space required by an algorithm for any input. Average case complexity. Average case complexity represents the expected time or space required by an algorithm for a random input. Now we'll see about complexity summary. The first one is selection sort. The best case is big O n square. Average case is big O n square. And the worst case is big O n square. The next one is insertion sort. Best case is big O n square. Worst case is big O n square. Average case is big O n square. The next one we'll see about bubble sort. Best case is big O n square. Average case is big O n square. And the worst case is big O n square. We'll see about merge sort. Best case is big O n log 2n. Worst case is big O n log 2n. And the average case is big O n log 2n. We'll see about quick sort. Best case is big O n log 2n. Worst case is big O n square. And the average case is big O n log 2n. The next one is tree sort. Best case is big O n log 2n. Worst case is big O n square. And the average case is big O n log 2n. We'll see the importance of performance analysis. Performance analysis helps in comparing different algorithms and selecting the most efficient one. It allows us to anticipate the behavior of an algorithm on different input size. By understanding time and space complexity, we can optimize algorithms and improve overall performance. Conclusion. Performance analysis is crucial for understanding the efficiency of algorithms. Estimating time and space complexity helps in predicting the performance of an algorithm. By optimizing algorithms based on complexity analysis, we can improve efficiency and save the resources. Thank you guys. We'll see in next session.